Deep Learning Part 1: What Deep Learning Really Is. Before a single line of code, one idea: a neural network is not magic, it is a function. Let's define it precisely and build it from nothing. Start with the object itself. A neural network is a function. It takes an input, x, and returns an output. And it is controlled by a set of numbers we call parameters, the Greek letter theta. We write it f theta of x. The shape of f is fixed by the architecture. The parameters theta are free to change. Deep learning is nothing more than the search for the parameters that make this function do something useful. Every idea ahead is detail on top of that one sentence. First, what flows through it? The input x is a vector, just a list of numbers. An image is its pixels unrolled into a long column, a sentence a list of token numbers. Here a tiny input, two numbers, a single point in two-dimensional space. The output is a vector too, a predicted price or the probability of each class. So the network is a map from one vector space to another, numbers in, numbers out. How do we know what useful means? We are handed data, a set of examples. Each one an input xi paired with the answer we want, yin of them. The goal becomes exact. Choose theta so that f theta of xi is close to yi for every example. We turn closeness into a single number, the loss, the average error across all examples. L of theta equals 1 over n times the sum over I of the error between f theta of xi and yi. Learning is minimizing that number. Notice what we search over and what we do not. The form of the function is frozen. We invent no new operations. We only turn the knobs theta, living in a space of p real numbers. Watch one knob move. As theta changes, the same function sweeps through a whole family of shapes. Training picks one member of this family. So the real question is, how rich is the family? Begin with the simplest family, the linear model. F of x equals wx plus b. W is a matrix of weights, b is a vector, the bias. If the input has n numbers and the output m, then w is m by n and b has m entries. Those weights and biases are the parameters. Count them and you have counted the whole model. It is the humblest network, and it already reveals the central problem. Here is a task the linear model cannot solve. Exclusive OR. 4 points, opposite corners share a label. Gold points want one answer, cyan points the other. No straight line separates gold from cyan. Rotate the boundary however you like. The best any single line achieves is 3 of the 4 correct, 75%, it is stuck. The linear family is simply too poor. You might hope that stacking linear layers helps. It does not, and the reason is worth seeing. Apply one linear map, then another. W2 times W1x plus B1 plus B2. Multiply it out, it equals W2 W1 times x plus a constant. But W2 W1 is just another matrix. 2 linear layers collapse into a single one, 100 would too. Depth by itself buys nothing, something nonlinear must sit in between. So we insert a nonlinearity. Take the rectifier, ReLU of z returns z when it is positive and 0 otherwise, a single kink. That kink is enough. With just 2 hidden units, ReLU solves exclusive or exactly. The output is ReLU of x1 plus x2 minus 2 times ReLU of x1 plus x2 minus 1. Feed in the four corners, 0, 1, 1, 0. Exactly exclusive, or a bend the straight line never had. Look at what that buys us geometrically. The two hidden units carve the plane into regions. Their combination bends a boundary that a straight line could never trace. Now the gold corners sit on one side, the cyan corners on the other. Cleanly separated. One nonlinearity turned an impossible problem into an easy one. That is the entire reason deep networks exist. Now the atom of the network, one neuron. It forms a weighted sum of its inputs plus a bias, z equals w dot x plus b. Then squashes it through a nonlinearity, a equals sigma of z. Concretely, inputs 1 and 2, weights 1/2 and -1, bias 0.3. The weighted sum z is -1.2. Through the sigmoid, the activation is 0.23. One number out of each neuron, that is all a network is made of. Stack neurons side by side and you get a layer. Every neuron reads the same input with its own weights. Stacking their weight rows gives the matrix W. One matrix multiply computes the entire layer at once. H equals sigma of Wx plus b applied element by element. 2 inputs into 3 neurons, W is 3 by 2, outcome 3 activations. This is why hardware loves neural nets. A layer is a matrix multiply. How many parameters does a real network hold? Take a small one, 784 inputs, a hidden layer of 256, then 10 outputs. The first weight matrix alone is 256 times 784. Add its biases and the second layer on top. The total is just over 200,000 numbers. 203,530. And that is tiny, modern models hold billions. Now the full picture, depth. A deep network is a composition of these layers. F equals FL after FL-1 all the way down to F1. Each layer feeds the next. The output of one becomes the input of the following. Layer L computes sigma of WLH plus B. The parameters theta are all the weight matrices and biases, gathered together. Depth is just how many times we repeat the pattern. Running the network is called the forward pass. The input enters at the left. Layer 1 transforms it into a first set of activations. Layer 2 reads those and produces the next. On through the stack until the final layer emits the prediction. Just matrix multiplies and nonlinearities in sequence. We will trace it in full in part 2. So how rich can these functions be? The universal approximation theorem. A network with a single hidden layer given enough units can approximate any continuous function on a bounded region to any accuracy you demand. Watch it happen. Here is a smooth target curve. With 2 units, a crude piecewise fit, the largest gap is wide. Double to 4 units, the gap shrinks. 8 units, closer still. More units, less error without limit. If one layer already suffices, why go deep? Because depth is exponentially more efficient. Take a layer that folds the line in half, a single triangle, 1 peak. Compose it with itself, 1 peak becomes 2. Compose again, 2 become 4. Every added layer doubles the structure for free. To match that by widening, you would add units by hand, exponentially many. Depth gets it for nothing. There is a deeper shift hiding here. Classical machine learning fed hand-designed features into a simple classifier. A human decided what mattered. A deep network learns the features itself. Early layers discover edges, middle layers parts, later layers whole objects. Nobody programmed that hierarchy. It emerged purely from minimizing the loss. This is representation learning. It is the real reason depth won. But richer is not always better. A family too simple cannot fit the data, it underfits. A family too rich memorizes the noise and fails on new examples, it overfits. The art is matching capacity to the data you have. Enough flexibility to capture the pattern, not so much that it learns the accidents. We return to this balance in Part 6. One property makes all of this trainable. The function must be differentiable in its parameters. Nudge any weight a little and the loss must change smoothly, it must never jump. That smoothness is exactly what lets us compute a gradient. A direction to move every parameter at once. It is why we choose smooth pieces, matrix multiplies and gentle nonlinearities, not hard discrete switches. We have the function, now how does it learn? Return to the loss L of theta. It is a landscape over the space of parameters, high where the network is wrong, low where it is right. We descend it, theta becomes theta minus eta times grad. Eta is the learning rate, the size of each step. Take a starting point and step downhill again and again. Watch the loss fall toward zero. What exactly is that gradient? It is the vector of partial derivatives of the loss, one for every parameter. Each entry answers a local question. If I nudge this one weight, how much does the loss change? Collected together, the gradient points in the direction of steepest increase. So we step the opposite way, steepest descent. The entire craft of training is estimating this one vector, cheaply and well. Picture the landscape in 3 dimensions. 2 parameters on the floor, the loss is height, a bowl. Gradient descent is a ball released on the surface, rolling toward the bottom. Real networks have millions of parameters, a surface we cannot draw, but the rule is identical, follow the slope down. Computing that slope for millions of parameters at once is backpropagation. That is Part 4. One question remains, these ideas are decades old, why did they work only recently? 3 things arrived together. Data at internet scale, millions of labeled examples. Compute, the graphics chip, running thousands of multiplications in parallel. And automatic differentiation, which computes every gradient exactly at almost no cost. The theory had waited, the ingredients simply did not exist, now they do. So the whole of Part 1 in one line. A deep network is a differentiable parameterized function, and learning is gradient-based optimization of its parameters against data. Everything ahead is that single idea made concrete. Next, Part 2, we build the neuron and push real data through it, forward propagation.